Welcome back, ladies and gentlemen. Welcome back. Welcome back to our second session. We will continue our agenda with afternoon session. So those who are not yet joining the Zoom account, please join. And I would like to also remind all of the paper presenters to join the online Zoom to be able to join the parallel session. But before we go to the parallel session, we will have the second main session with the afternoon session. And this session will invite Professor Dr. Hero Jan Heres from University of Groningen and Netherlands, and Dr. Wan Azmin bin Wan Hamzah from University Malaysia Pahang, Malaysia. And our moderator for this session is Miss Athanasia Amanda Septefani, PhD, to lead the session. For your information, Athanasia Amanda Septefani is one of the lecturer in Chemical Engineering Study Program in ITI. She is also currently researcher in National Research and Innovation Agency, or BRIN. She gained her PhD in Bioengineering and Nanotechnology from University of Queensland in 2017. Recently she got several achievements on research areas. She was the first winner of Merck Young Scientist Award in 2021. She also won L'Oreal UNESCO Women in Science in 2018. Her recent research publication is titled 3D Printing of Fully Cellulose-Based Hydrogels by Digital Light Processing. Without further ado, please welcome Ms. Amanda Septefani. The stage, the screen, and the time is yours. Have applause, everyone.
Thank you very much, Ms. Garisi, for a very nice introduction. It is such a pleasure for me to be here as a moderator for the afternoon session. So as previously mentioned by Ms. Garisi, there are two speakers in this afternoon session. For the first speaker, distinguished speaker, is Professor Hero Jan Heres. Good morning, Professor. Okay, it's such a pleasure to have you here. So,
thank you very much.
Yes. So before we begin our presentation, let me introduce Professor Hero Jan Heres. So Professor Heres did his PhD in chemical engineering in 1990 in Groningen University, and then he continued did his postdoctoral in the group of Professor G.M. Brown at the University of Oxford. Then he also had experiences in the shell research, and then he continued to be assistant professor in the Department of Chemical Engineering, University of Groningen, and received his full professor in 2003 in the green chemical reaction engineering. His main research is about development of the highly intensified catalytic technology, especially conversion of the biomass to biofuel and several bio-based chemicals. Professor Heres also published a lot of papers in reputed journals, where he also appointed as the associate editor in the Journal of Fuel Processing and Technology. He also one of the most cited author in the Department of Chemical Engineering. It's such a very pleasure to have you. So Professor Heres, please give a big applause for Professor Heres, and the time is yours.
Thank you very much for this very kind introduction. It's really a pleasure for me to give a presentation here. And I also would like to thank the organizers for giving me the opportunity to do so. I will share my screen. Can you all see my screen now?
Yes.
Super.
Great.
Okay, thank you very much. So the talk for today will be particularly focused about renewable chemicals and using a particular technology. And that technology I will go to explain is a technology called pyrolysis. On this slide, you see our main building of the University of Groningen. We're situated in the Netherlands, in the north of the Netherlands, close to Germany, and that's where we're located. What I'm going to talk about, first of all, I will give a short introduction about the challenges for the chemical industry in the future. I will say something about options to green up the chemical industry. Then I will move on to a particular example where I use pyrolysis technology to actually make renewable chemicals. And I will do that for two feedstocks. First of all, an example for biomass. And then I will also give an example for waste polyolefinic plastics. And I will end with some conclusions. Now, first of all, what products are we talking about? I talk about chemicals, renewable chemicals. What chemicals are we talking about? Well, we're talking about the chemicals which are used for the manufacturing of a lot of daily life products. And you have to think about carpets, you have to think about paints, you have to think about bottles, polymeric bottles like a PET, and you have to think about adhesives. So what we're going to talk about is the chemicals which are used to make these consumer products. If we look at the moment, all these products are mostly made 90% from fossil resources, like crude oil, like natural gas, and like coal. And this is an example for the crude oil, using that as a feed. If we have our crude oil feeds, it is actually fractionated in a distillation column. What is coming out of the distillation column are certain fractions, depending on carbon number. And the low carbon number fraction, particularly this one, the naphtha fraction, that is the input for the current petrochemical industry. And this industry actually makes these consumer products, like the plastics, like the paints, etc. Well, we all know that we have a major issue with the use of these fossil resources. And we all know the CO2 issues, we know the greenhouse gas emissions, we know the effects on our climate. I don't have to explain to that. But as a response, there are now all kinds of policies and incentives to actually reduce the amount of CO2 in the atmosphere. And of course, what we aim for actually is CO2 neutral societies in 2050. Now, how to achieve this? This is a major transition. We have to move away our hunger for fossil resources to something new, to alternative feeds. And what could be these alternative feeds? Well, what these could be are the following. First of all, what we could think about is biomass. So replace part of the fossil resources with biomass, and particularly waste biomass sources, for instance, from the agricultural sector. Another form of renewable carbon is actually the use of waste plastics. You all know it's a major issue at the moment. Most of these plastics end up in landfills or even in rivers, like in Indonesia, and cause a lot of pollution. So what would be nice to use this also as a feedstock for these consumer type products. And finally, maybe not obvious, but what's coming out of these chimneys is a lot of CO2. And CO2 is also a very interesting source, starting material, a feedstock to make new chemicals and fuels. So also CO2 from particularly exhausts is a really nice starting material, a renewable form of carbon to make chemicals. Now, if we would like to promote this transition, so if we would like to move away from these fossil resources to actually these new renewable type of carbon sources, what are then the challenges? Now, first of all, we have to consider that the feeds are sustainable. And what I mean is they do not harm our planet. And for instance, when you look at biomass, you do not want that these biomass sources compete with food. In other words, you don't want to use food products to make these bio-based chemicals. Second major issue is the techno-economic feasibility. Can we make these chemicals from renewable resources at a price which is actually in the same ball game as now for the fossil resources, as now the products which are now on the market? Also very important are logistics. Crude oil and gas often comes from point sources. It's by far we have to set up the logistics, particularly for biomass, on a global scale, as well also for plastic recyclates, which is not easy. And finally, we have to demonstrate and scale up these new technologies. And actually, this is also not easy. Time-consuming process, and from an invention to full-scale operation often takes more than 10 years time. So we have to consider that time is also very important and a major challenge. Now, if we look to these renewable forms of carbons, and which would be nice to use as feedstock for the chemical industry, we can think so about CO2, biomass, and waste plastics. And how does this work? We have here our renewable carbon. You can actually use them to make chemicals and go for consumer products. One form of consumer products are plastics. The idea will be that you can recycle these plastics and then also get back in the form of renewable carbon. What I'm going to talk about is particularly biomass as a source of renewable carbon, and I'm going to talk about waste plastics as a source for renewable carbon. The technology I'm going to show you, as already promised, is a technology called pyrolysis. And I will explain a bit later what actually pyrolysis is. The idea will be that we convert these renewable carbon sources, biomass and plastic waste, into intermediate products which can be used to turn into chemicals. And in the case of biomass, the intermediate products you get after pyrolysis is pyrolysis oil. And when you do plastic waste, the product we're interested in is plastic naphtha. Pyrolysis you can either do without a catalyst, so thermally, or you can also use catalyst to actually play around with the yields and also with the products you actually make. Now, let's start with biomass. So have a look at biomass and use pyrolysis to turn that into a liquid form, into a liquid oil. Now, what is biomass? What is pyrolysis? Actually, it's relatively simple. It's just taking a biomass source, in this case, wood chips, and you heat them up in an inert atmosphere, so without oxygen, you don't burn it. And actually what's happening then is the biopolymers in these biomass, like cellulose, hemicellulose, and lignin, they are depolymerized, cut into small pieces, and these pieces end up in the vapor phase, small low molecular weight components. You then rapidly condense the vapors, and what you get then is a pyrolysis oil. That's the desired product. So what you actually have done in this case, you made a liquid biomass. And what are the byproducts? The byproducts are char. You always get a bit of char. And you also get some non-condensable gases like CO2 and CO, often a bit of hydrogen. How does this pyrolysis process work? This is an example. So here you have your biomass feed, for instance, sand, and you bring that in a suitable reactor where you heat up the biomass very rapidly in the absence of oxygen for 500 degrees. What you get then is a vapor. You cool down the vapor and you collect the oil and you transport and distribute it. This oil is not a crude fossil oil. It has a totally different composition. It's oxygenated, contains a bit of water, but you can use it for a number of applications. The interesting part from a chemical engineering point of view is that actually you do you run this reactor, often in the presence of a heat carrier. And a mostly used heat carrier is sand. So the reactor is also fed with heated sand, brought together with the biomass source. And in that way, the process goes more effectively and you get more of the desired vapors. What's coming out of the reactor is actually sand and the char. And char, about 10%, is a byproduct. But you use this very effectively in this process because what you do in the next step, you contact the sand and the char with air in a combustor, and there you actually burn off the char. And what you generate then is heat. So you heat up the sand again and recycle it back to the reactor. So this process is operated with a sand recycle and to actually have your heat management of the reactor in place. Now, the pyrolysis technology, what's the commercial status? It is actually now a commercial. It is run on a commercial scale in the Netherlands. And here you see the factory. It's close to Hengelo in the east parts of the Netherlands. And there are also 2 new pyrolysis plants recently being established in Sweden and also in Finland. So this is commercial technology. Now, if this is commercial technology, a question always arises, can you still do research about pyrolysis? And the answer is yes. And this is just an example from our own lab, where we still do a lot of work on to improve the pyrolysis process, to get higher yields of your desired pyrolysis oil. And this is just an experimental setup in our laboratory, where we on a continuous scale try to improve the pyrolysis process using what we call the molten salt technology. And in that way, actually, we can improve the yields of the various oils we obtain in this process. So this is a small demonstration unit in our laboratory. Now, what we're interested in this presentation is to convert biomass into chemicals. We were interested in chemicals. And I will give you an example of chemicals we're particularly interested in. And the chemicals we're interested in are what we call aromatics: benzene, toluene, and xylenes. And these are actually existing chemicals in our petrochemical industry. So also in Indonesia, these are made on large scale, and a major application are used as polymers, as polymer precursors, for instance, to make PET bottles. These aromatics at the moment are made from crude oil in a conventional oil refinery. What would be nice if we would be able to also use biomass as a source for these aromatics. Would that be possible? Now, in this case, pyrolysis also plays a role. And I will show you that we indeed can make these aromatics from biomass sources. And in that way, green up the molecules here, make them from a green resource. And so also the polymers you make then are made from a green renewable carbon starting material. Now let's have a look. How can we do this? What we have to do then is what we call catalytic pyrolysis. So it is a pyrolysis, like I just showed you, but now what you do this in the presence of a catalyst. And these catalysts are often zeolites, a very acidic, Bronsted acidic catalyst, and which you then add together with the biomass in your pyrolysis process. And the aim is now that the liquid, the pyrolysis oil, contains a large amount of these bio-based chemicals, benzene, toluene, and xylene. How does this work? Here again, you see the pyrolysis process, like I just showed you, here the reactor. And you can do this also in the presence of catalyst to enrich this oil in the desired benzene, toluene, and xylene. Where can you add catalyst? Well, you can add them in the reactor. That's what we call in situ catalytic pyrolysis. And you can also add catalyst in the vapor stream, and we call it ex situ catalytic pyrolysis. What we particularly do is ex situ catalytic pyrolysis. So we do a lot of work on converting biomass sources into benzene, toluene, xylene using catalytic pyrolysis. The main issue there is that techno-economically, it's not yet competitive with fossil resources. So what we did a lot of work the last 10 years is to identify cheap biomass sources. The cheaper the biomass source, of course, and the cheaper the products will be. What we're mainly using also is to improve the yields of the BTX and to get as much as BTX out of the process as possible. How can you do that? Play with reaction condition, temperature, resonance times, look at very robust and stable catalysts, so modify the zeolites that they get, are they more robust and stable, and also introduce recycle concepts to also have, when you have byproducts, to recycle them back and increase the yields of BTX. And we also did some scale-up work, and I will show you an example. Now, most of the work in the lab, when we would like to improve this process, we actually do this on a very small scale. So this is what we do in our laboratory to convert biomass in benzene, toluene, and xylene. And this is what we call a tandem microreactor. What you see here is a gas chromatograph here on the bottom, and on top of this you see a tandem microreactor. How does this work? What we do here is an injection system on top. We here inject our biomass source in this part, and this is the pyrolysis reactor. So here the biomass is pyrolyzed and you get the vapor. Then the vapor is transported through a transport line to the reactor, and in this reactor you have your catalyst present. Then the outlet stream of this second reactor is actually brought into the GC, and that allows you to identify the components which are in this vapor stream. And when you do this properly, you actually get a GC chromatogram like this, where you have the benzene, the toluene, and the various xylenes in a certain yield. Now, if you do this for instance, crude glycerol, and we use particularly crude glycerol because this is a byproduct from the biodiesel industry. So it would be nice to give value to that, and maybe we would be able to actually convert it into benzene, toluene, and xylene. Now, if you do, for instance, experiments with crude glycerol, what you actually get is 35% of an oil, and this oil roughly contains about 17 weight percent of benzene, toluene, and xylene, and the remainder are higher aromatics. So we're able to convert crude glycerol to benzene, toluene, and xylene, which is now green, and yields roughly up to 17 weight percent. This is just an example of how to convert an interesting bio-based material into green benzene, toluene, and xylene. Now, we also scale this up. So what you see here is what we do in our laboratory. We do it on milligram scale. You can also do it on a slightly larger scale. This is a demo unit we have in our laboratory also at a scale of 500 grams per hour. And we also built a pilot plant on our campus at tens of kilograms of hour per scale. And this was done by the company BioBTX. And we also showed that the conversion of glycerol to BTX also worked really on this scale and with minor operational issues. Now, my final example is how can we use waste plastics as a form of renewable carbon to make chemicals? Now, first of all, we all know the issues, right, with waste plastics. These are just examples. I've been in Bali many times in Indonesia, and all the time when I'm in Bali in February, the beaches are covered with plastics. It's probably related to the currents in the sea, but you always see it. And of course, this is not something you want to show to the tourists. These plastics also have a very negative effect on life, sea life, and also on birds. And this is also a well-known example. Now, one of the ways to reduce the impact of plastics on our environment is actually to recycle it. So, and this is actually let's say the typical production chain, the value chain of plastics. Here we have our virgin plastics. We refine it, we polymerize it, we formulate it, we process it, we packaging it, and then we use it as a consumer product. Now, at the moment, most of these consumer products, after use, are discarded in landfills. And actually, what we would like to do is recycle the plastics. Now, there are many ways to recycle. You can have very short recycles. And for instance, you can do this with certain plastics, but you also could go back more into the loop. And then you have longer pathways, longer recycle loops. The most ideal case is where these loops are very small, because that often means that the energy input is the smallest. The disadvantage of smaller, for instance, mechanical recycling, is that it's very difficult to get back the original properties of the plastics. So what you typically see is for polyolefins, like polyethylene and polypropylene, the only way is to go back to depolymerize these materials and go back to the monomeric stage. So actually the idea will be to go back, depolymerize them, and actually go back to a stage where you are preferably in the monomeric form. Now, if we look to the chemical recycling, we actually have a number of ways to do so. We have the thermochemical way, high temperature processes, 400 degrees plus, like pyrolysis and gasification. Some chemical recycling processes can be done based on solvents. And for instance, some polymers you can actually break down in combination with solvents, like PET, and so it's polyesters. It works quite nice. And even there are also some ways to convert plastics back to the monomers using enzymes. And also PET is a well-known example for that. I will give, of course, here an example for pyrolysis. So what's the idea here? We have our plastic, and after use, it's a waste plastic. We pyrolyze it, then we break it down into low molecular weight fragments, and this renewable carbon coming out is actually used again for chemicals. So you get a kind of a loop. So if we look at polyolefins, like polyethylene, it's a long chain polymer. We like to break it down with pyrolysis into low molecular weight components. Is this possible? Yeah, this is really possible. So again, the pyrolysis technology plays a major role here. So what you do, you take your waste plastic, heat it up to 400 or 500 degrees in a pyrolysis reactor. There the plastic is broken down in small molecular weight fragments. It's ending up in a vapor phase. You condense it, and actually what you get is what we call a plastic naphtha. So it's a low molecular weight fraction which mimics naphtha. So a carbon number between, on average, C8. Now, what's the use then of this naphtha? What you can actually do then is use this again in a conventional oil refinery. So what you actually do is you take a waste plastic, pyrolyze it, get a naphtha, and recycle it back into an existing oil refinery. So that will be a nice way to recycle these polyolefinic plastics. The picture you see here is actually not a picture from the internet. This is a picture from the pilot plant we actually have on our campus. So we also pyrolyze plastics in this unit and to make this synthetic naphtha and to use this then in an oil refinery. Well, if you look to the oil refinery, what we actually aim for is then introduce somewhere this plastic naphtha, and this product from plastic pyrolysis. And one of the entry points could be actually here. The entry points could also be here. That depends a bit on the quality and the level of impurities in this plastic naphtha. Is this of interest? So, and what is the technological readiness of this technology to make naphtha from recycled plastics? Now, there's a huge interest, particularly from the petrochemical industry at the moment. The Shell has a fantastic ambition in this field. Dow is interested. SABIC is doing a lot of work in plastic recycling, and also ExxonMobil is building plants for recycled plastics. So this is really a very hot topic, how to convert waste polyolefinic plastics into a synthetic naphtha. So conclusion of my presentation, I've shown you that we can replace fossil resources by actually renewable forms of carbon, and we consider CO2. I did not discuss in this presentation, but what I did discuss was the use of biomass and the use of recycled plastics. The technology I presented here, which could be very suitable, is pyrolysis. Well, if we're going to use this on large scale to make our societies carbon neutral, this will require major investments, a lot of research and development, come up with innovation. I think this is also one of the tasks for us as universities, as students, as staff, to come up with new ideas, how to make this very effective. And what also is required is not only the technology needs to be developed, but there are many, many more stakeholders involved, like the public, like the governments, like the policymakers, etc., etc. I'd like to make some acknowledgements, not an extensive list. This is a picture of the pilot plant and the people involved on our campus to use pyrolysis to make chemicals in synthetic naphtha. And this is a relatively new picture from the research group in chemical engineering in Groningen during one of our lab outings 2 years ago. And I thank you very much for your kind attention.
Thank you very much, Professor Hires. Let's please give a big applause for Professor Hires. Okay, we have listened what Professor Hires shared to us about the potential of the new renewables carbon resources such as CO2, and then he also explained about the biomass and plastic waste. As we know that basically all of these material as the resources is also available in Indonesia. So I guess that it will be trigger a lot of questions from the participants. So I now open the discussion, but from the virtual Zoom, ada ya? No. Or maybe the participant who attend online now. Do you have any question for Professor Hires? Oh, Professor Hires, I'm curious between the biomass waste as well as the plastic waste. I think these two of the resources is giving a big problem as well in Indonesia to handle and to do the valorization to produce the value-added products such as, like you explained, chemicals and then bio oils. So what do you think about these two materials? Which one that is having a more opportunity to be developed into the large scale as you explained?
Yeah, I think there's not a question of which is better or which is worse. I think there's room for both of them. When we would like to make this transition to come to CO2 neutral societies, we have to. There's not one pathway which will be which will give us the solution. We need to look at all the opportunities we have, and we have to investigate them. And there will not be one; there will be many which will offer us the solutions for the future.
Okay, I see. So, what type of biomass that you have developed previously in your previous research? What type of biomass?
We used many types of biomass. I've done many projects also together with Indonesia. In Indonesia, we particularly look at waste from the jatropha processing industry, from the palm oil industry.
Yes.
We looked, for instance, at waste products from rubber plantations. And we looked at byproduct valorization like rubber seeds, and we use them a lot. The glycerol is a well-known example as a byproduct from the biodiesel industry. We used a lot at, and we also looked a lot at the pulp and paper industry because the pulp and paper industry also produce a waste product, byproduct, which is called black liquor. And black liquor contains a lot of lignin, and you can use them very nicely for all types of fuels and chemicals.
Okay, great. We have also the question in the chat room, Professor Hires. So it's from Amar. He's asking about how is your experience in the Netherlands for the use of bioenergy in Netherlands? Is that easy to apply into the commercial, I think, instead of publics?
So what we see at the moment, biomass is particularly used in existing coal-fired power plants. So co-feeding of biomass, like wood chips, into coal-fired power plants, that's at the moment happening a lot. And about 10% of the electricity generated in the Netherlands comes from biomass at the moment. And that's mainly by co-feeding coal-fired power plants.
Okay. I think we still have a lot of discussion to do, but because of the time frame, my apologies. I think we should end the session, but it's really great to having you. Maybe if everyone here, participant or the lecturer in the ET that we want to collaborate with Professor Hires, maybe we can talk about more, and you can contact Professor Hires in the details that you can ask to the committee. For the appreciation, Professor Hires, we have the virtual certificate. Committee, please show the virtual certificate. Oh yeah, here is the virtual certificate. We will send to you as well via email, but it's nothing can thank about your presence here, and thank you very much. And we will see you next time. Thank you very much.
It was my pleasure. It was my pleasure. Thank you very much.
Professor Hires, once more. Okay. Now we are moving to the second presenter. I think Professor Wan Asmi has been here. Hello, Professor Wan Asmi.
Hello. Hello.
Hello, Professor Wan Asmi. It's very nice having you here.
Yeah. Thank you.
This is our last speaker, but not least, of course, Professor Wan Asmi bin Wan Hamzah. So he did his PhD in mechanical engineering in 2015 from the University Malaysia Pahang. His working experiences in a University Malaysia Pahang has been started since 2008, where he is now a professor in University of Malaysia Pahang. I think in 2022, so he's just appointed, right, Professor?
Yes, correct. Just appointed.
Professor appointment.
Yeah.
His field of research is a massive. So from thermofluid engineering, automotive, nanotechnology, and then cooling system, lubricant, air conditioning system, solar system, tribology, and heat transfer. And I can't read all of the awards, but I think a lot of awards you have received. And some of them that has been received recently, he received a Malaysian Research Star Award in 2019 in the top as a prominent topics in research and young researcher, and also he is a top 2 scientist of the world ranking that I think organized by Stanford University in 2019 and 2020. What a great achievement, Professor Wan Hasmi. So in this opportunity, Professor Wan Hasmi will present about the fast pyrolysis. I think pretty similar with our previous professor here's topics, about a promising technology for renewable carbon conversion. So without further ado, please welcome Professor Wan Hasmi. The time is yours.
Okay, thank you, moderator. So first of all, I want to share my screen. Okay. Okay, can you verify? Can you see my screen? Is it my screen is visible to everyone?
Yes, please put in the full screen, maybe, Professor.
Okay, hold on. Okay.
Full screen.
Okay. So please give me a minute. Here. Okay. Okay. So is it clear? So this is the first page of my slide presentation. So can I start now?
Sure.
Okay. So Assalamualaikum and good afternoon to all participants, to all participants today. First of all, I would like to thank organizer for the first international conference on advanced technology in chemical engineering for the invitation for me to be an invited speaker for this event. And also thank you for the moderator to introduce me at the beginning of the session. And also I can see Honorable Rector also in the session today. So thank you also Bapak Rector for the invitation for me. In fact, I'm also actually my field is mechanical engineering. But what I'm doing right now, actually, in the nanotechnology, specifically for the nanoparticle dispersion technology. So we call as a nanofluids. So which is, I think the exact title today for my my talk today is on the development of advanced technology in nanofluids. So this is the given title for me lah today, and also I will also add some more information on the international research collaboration opportunity, which is I'm trying to focus on the collaboration between Malaysia and also Indonesia. So not many lah, but I'm trying to give some brief idea about some of the opportunity lah for us to can have a grant collaboration, especially for the grant lah, between Malaysia and also Indonesia. So my name is Wan Azmi Hamzah, and also the co-author is actually Associate Professor Anwar Ilma Ramadan from UMJ. So he's my PhD student right now. So will complete his PhD very soon. Okay. So you can see the detail of the nanoparticle dispersion technology in this website. This is my research website, www.nanodistech.com. So which is in this website, I share everything lah about the technology, which is I call as nanoparticle dispersion technology. Okay. So this is a little bit about my research profile, but I don't want to focus more on this part. So because the moderator already give a brief idea about my my research background, so but I just want to highlight about the area of specialization, which is on the nanoparticle dispersion technology. So I call as nanolubricants, and also nanocoolant, also nanopin. So it's depend to the what kind of base fluid that we disperse the nanoparticle. If you disperse in lubricant, then we call as nanolubricant. So if we disperse in the base coolant, then we call as nanocoolant. And also we have another technology, which is we disperse the nanoparticle in the paint. It might be automotive paint and also house paint lah. So it's depend the base paint that we want to study lah. So this kind of technology is already started, I think, for more than 20 or 30 years back lah. So but we try to look at on the side of the nanocoolant, which is on nanofluid. We want to focus on the heat transfer issue lah. The issue on the heat transfer. Okay, so just take a look on the general background of study about the nanofluid. So just when we talk about the the nanofluid or nanocoolant, we have to focus on the problem on the heating and cooling process. Normally we are using the conventional heat transfer fluid. Most of the time, normally we are using water as a base, as a coolant, or we are using oil or ethylene glycol or any other type of glycol lah. So, but what happened when we improve the the technology? For example, we improve the compact PCs or compact laptop computer, so it run very fast, right? So what happened? So they have a limitation with the conventional heat transfer fluid. The conventional heat transfer fluid is remain the same. But the problem issue is because of the compactness of the device. So what happened? We need to have a better heat transfer fluids lah, in order to extract the heat from the system to the outside lah. So then, if we didn't do that, it will give effect to the performance of the device. So that's the one of the big issue lah. So the researcher tried to introduce what we call as a new engineer fluid. So which is we try to use a nanoparticle to disperse in the base fluid, in the heat transfer fluid. Initially, I think in 80s or 90s, so most of the researchers, they try to disperse micro-sized particle. What happened? There is a problem with the sedimentation, where there's problem with the stability. So, and then suddenly, early 90s, so the first researcher from Japan, actually, in 1993. So this, his name is Masuda, which is he has a team lah, Masuda et al. So they, the first published paper that present the nano fluids actually. So that one they present the just only up to the properties, up to the properties or characterization level for the nanofluid. But the first paper that present the heat transfer study on the nanofluid itself is the Choi in 1995. But I recognize Masuda as the pioneer in this topic lah from Japan. One of the issue with the Japanese, so they didn't, they have their own journal, they didn't release to the outside. So there is no wonder that most of the people they recognize 1995 from Choi, which is as the first papers, as the fathers of the papers lah. I mean the topic in this study, but it is started from 1993 from Japan. Okay, so they initially when they 1993 they use a mono nanofluid, we call it a monofluid, which is using a single nanoparticle they disperse in the base fluid. Okay, so what happened when they disperse nanoparticle, the first paper in 90s, so they claim that it is have an excellent suspension stability because in the nano size. So starting 90s, we have a technology to produce a nanoparticle, nano size, and then it have a very small pressure drop. In 1995, they claim that there is no significant pressure drop because of the small size of nanoparticle in the heat transfer system. So after 20 years, we study about the mono nanofluid. Then we introduced in 2010s, 2010s. We introduced hybrid nanofluid, which is we mix between two different type of nanoparticle in one single base fluid. So we call it as a nanofluid, hybrid nanofluids. Again, then the recent type of nanofluid, we move to the ternary. So we try to mix three type of nanoparticle in one single base fluids. Then we claim as a ternary nanofluid. So the good things about the suspension of two or more dissimilar nanoparticle in the base fluid is it is expected to yield a better characterization in terms of the heat transfer properties, in terms of the rheological properties compared to the single nanofluid, according to Lee et al. And others lah. Okay, so and it is also proven in my research. It also proven in my. I will show you later on lah. Okay, so just take a look on the general issue in heat transfer. So what happened? We can see that the rising demand in power consumption, as just explained before, which is we have a miniature heat transfer system compactness. It will reduce the cost, and the reason why they want to make it smaller, it can reduce the cost and energy efficient, increase the efficiency. So what happened? If we didn't overcome the issue of the thermal performance, it will have issue with the drawback with the performance because of the issue with the heat transfer problem, right? Cooling system and so on. Then we have to improve it, because the issue is the conventional coolant. We have a low thermal conductivity. Then they have a certain limitation after we design an advanced device. So it will reduce the system performance and equipment life. So that's why we introduce mono nanofluid. So the existing mono nanofluid, it can improve the heat transfer, but the issue with the mono nanofluid, they have a limited stability, and then it have a thermal conductivity enhancement. But we try to improve it again and again. Okay, and then we try to introduce hybrid nanofluid, which is combine physical and chemical properties of two different type of material. Then again, this kind of hybrid nanofluid can improve heat transfer performance according to Sarka et al. And then it's have better thermal conductivity and so on. But the recent study in ternary, because hybrid is almost, I can say that hybrid is already, many papers already published in literature, but for the ternary nanofluid, it's limited in literature. And also from my student, my S3 student, confirmed that it have performed better in stability and also better thermophysical properties. And at the same time, we can introduce ternary nanofluid with green type of base fluid. So that one also one of the potential for the future research in this kind of topic. Okay, so we have a certain scope in this kind of research. Okay, so we have of course we have to do the literature or review study, and then we have a synthesized nanoparticle, which is the chemical engineering. I think quite interested to focus on this part, but because I'm from mechanical, so what happened? I'm focused on the preparation of nanofluid, where I procure the nanoparticle from the from other from the manufacturer. Then I disperse. I'm start from the dispersing of the nanoparticle in the base fluid, and then start to prepare nanofluid. And then number two, we move to the stability evaluation. Okay, we have to confirm that the nanofluid in the stable condition. So it's not just an easy task, right? We have to focus on the how to make it stable, and then we move to the characterization, because this is a new, when we disperse nanoparticle, we don't know how about the characteristic of the final solution. Then we have to characterize it, and then we have to do the evaluation. We have to do the measurement for the new kind of the properties, especially on the thermal properties, also physical properties. We have to measure it ourselves because this is a new type of fluid. And then finally, we have to confirm the final performance of the nanofluid in the heat transfer system. Depend to the application. If the solar application, then we have to test in solar. If the chemical process or in any cooling system, then we have to test it. That is the final stage. Maybe as a experimental work, simulation, also optimization. So we can do any kind of research lah for the last stage of the performance testing lah. Okay. And then so let us move to the nanofluid itself. So nanofluid actually we have to prepare the nanofluid have two different steps lah, two different ways of preparation. So we call as one-step preparation, also two-step preparation. So normally for one-step preparation, the chemical engineering researcher quite interested to do that. So this is a very good topic for the chemical engineering, which is a researcher, which is they can study on how to prepare, the nanofluid as a single step, from the bulk material. Then straightforward, they prepare the nanofluid in the liquid form. So that's what we call as one-step preparation. For the two-step preparation, because I'm from mechanical, we have a limited, limited knowledge on the chemical engineering or chemical, topic. Then we try to, the first step is to prepare the nanoparticle in powder forms. Then in the second step, we disperse that nanoparticle into the base solution. That's what I did in my research lah. But the issue in the two-step preparation, we have to do the what we call as the homogenization process lah, which is we have to make sure that the solution in the stable condition, because we are not just mix, just using a normal stirrer. It's not just a mixer. So we have to use a homogenizer step in order to make sure that the nanoparticle disperse well in the base solution. So after that, we have to do the stability test to confirm that the solution is stable. What happens if it just mix the nanoparticle with the base solution? Then what happens after even 5 minutes, it will settle down. So when you go to the system, heat transfer system, it will clog into the system. So it will not good actually. And in fact, the performance transfer also is not good if it is not in a good stability condition. So that's why we have to test it. And after that, we have to do the characterization and properties test. Okay. And then finally, we have to do the performance testing to make sure that it is to confirm that the heat transfer is performed better. Okay, they have a various application in heat exchanger, automotive, solar, manufacturing, chemical processes, and many more. So depend to the application. Depend to the application. So this is the research flow of the topic of nanofluid. So start from the preparation. So we have to measure the base fluid. We have to weigh it, stir by mechanical, then homogenizing by using ultrasonication or mechanical. So for this case, most of the time, I'm as a mechanical, researcher actually. When we want to use in the transfer system, we try to avoid using control pH or to alter the pH, because the alteration the pH control also one of the step to make sure that the nanofluid is in a stable condition. But what happens if we control the pH too acidic or too alkaline, it will give effect to the final application. So that's why for my study, actually, most of the time we are try to using the mechanical homogenization process using ultrasonication, also mechanical, because it will not change the pH of the solution itself. So should be better in the almost neutral lah, very plus minus 7 or 6 or 8. And then we move to the stability evaluation. They have a certain step by visual, ultrasonic spectrophotograph, zeta potential, TM, and FISEM. So we have to evaluate it. Okay, and then after that we move to the characterization, because we have to look at the properties in terms of the thermal properties and also physical properties. Most of the time we have to measure the thermal conductivity to look at to the thermal performance, and also viscosity to see how viscous the fluid, because when we add the nanoparticle, it will make it viscous. When viscous, it is not good to the heat transfer system, too viscous. So we have to minimize the increment of the viscosity, but we want to maximize the increment of thermal conductivity. That is the the issue lah with the nanofluid. It increase, but they have a drawback with the viscosity. Okay, then finally we have to go to the application. We have to test the heat transfer performance evaluation. We have to test the saving in terms of the heat transfer saving, energy saving, and also efficiency. And also we can do the optimization lah to select the best parameter lah in the study. Okay, so I have to move fast lah because the time is almost. Okay, so now we have a nanoparticle, then we have a base lubricant, base fluid. So we mix together. So after that, we just start with the mixing, normal mixing, physical mixing using a stirrer, biasa, normal stirrer. Then we move to the homogenization process lah. Most of the time, I'm using the ultrasonic bath. That is the best effective method lah in my study for the nanofluid. So we also can use high speed homogenizer. Also, it is effective for certain application. Okay, so this is the final solution of the nanofluid. So we have to make sure that it can be stable for maybe 1 month or 2 weeks or 1 month. It depends to the application itself. Okay, so actually for the stability evaluation, I think the chemical engineering researcher. So this is a very interesting topic lah for the chemical, because from my side we have a limitation in terms of the knowledge. So what we do is we try to using the mechanical homogenization in order to make sure that the nanoparticle can remain stable for 1 month, 2 months, 3 months, and so on. But you can see that after a certain time, you can see the sedimentation here. So this is sometimes it's not good for the heat transfer system later on. So we have to avoid. So it depends to the selection of the nanoparticle and also the selection of the base lubricant, base fluid. So this is very important lah. So we have to look at on this point of view. The final climax for the stability condition using zeta potential, that is the best indicator to measure the stability condition of the nanofluids. Okay, then they have a certain method lah for the stability evaluation from the mechanical point of view. We are using visual observation. We are using time to see the agglomeration. We are using UV spectral photometer. We can also measure. We have a certain step to do that because UVV is not for the stability itself, but we can using a relative method to make it as a as a stability device. And also we are using zeta potential and also density observation lah. We have a 5 method to confirm the stability condition. Okay, then we are using viscosity, viscometer to measure the viscosity, and also we are using thermoconductivity meter lah in order for us to measure the thermoconductivity of the nanofluids. Then it depends to the application. Some of the nanofluid we can measure the tribological, depend to the application. For the case of nanolubricant, we can measure also the tribology. It is depend to the application, but most of the time for the heat transfer, we focus on the viscosity and also thermoconductivity. Okay, then finally, we try to test for the heat transfer performance using, this is for the experimental work lah. So we are using forced convection heat transfer test rig. So this is in my lab. So we focus on this. It depends. If you want to test for the solar application, then we have another test rig lah for the solar and for others. It depends to the application of the final application of the heat transfer itself lah. Okay, this is the focus on how we run the experiment. So just to show the specific schematic diagram for the heat transfer performance. So this is the result. So we can see that even after 6 months, so there is no sedimentation. Okay, so even by visual, but visual is not a good indicator. We have to confirm. This is the qualitative. We have to confirm with the quantitative. So we also confirm with the TM. So you see the mono. This is the mono nanoparticle nanofluid. Single hybrid nanofluid. We can see 2 different type of nanoparticle. Then finally we have a three type of nanoparticle ternary for the ternary nanofluids. So we can confirm that we have a titanium oxide, silicon dioxide, and also alumina. Different. We have to confirm it. The availability of these 3 type of nanoparticle in the solution. We cannot just claim, simply say we have a 3 type of nanofluid and nanoparticle. So we have to confirm it using that. So this is the quantitative using UV spectral photometer. Still, if it is very close to 1, so means that it is stable. So we have a difference at 2 hours sonication time. So it is the most stable solution. Without sonication, it keep dropping, right? So we can confirm that with sonication, with the sonication time, with the ultrasonication, then it will improve the stability. Okay, then this is zeta potential more than 60, so it shows a stable solution. So this is how we confirm the stability condition of the nanofluid. And then we go to the thermoconductivity of the nanofluid, the first thermal properties. So this is the baseline. This is the baseline. We can confirm that all the nanofluid is improved the thermal conductivity of the base fluid. So this is from this graph, you can confirm that. Okay, and also for the dynamic viscosity or kinematic viscosity, it also improved. This is not good, but we have to minimize the increment of the viscosity because it will affect to the pressure drop or friction factor of the final.
Hello, Professor Wanasmi. I think the connection is interrupted.
So, pardon. Okay, and then at 0.02%, so we can see that it is the lowest, which is the good for the tribological. Okay, last, just want to show you the heat transfer analysis. So we can see that this is the nanofluid, this is the baseline. So we can see that all the nanofluid have a heat transfer coefficient. It's better than the baseline, better than the base weight. So you can confirm that at different temperature. This is the 30 degrees Celsius, 50 degrees Celsius, and also 70 degrees Celsius. So means that the nanofluid is perform better than the base fluid itself in terms of the even up to 128, more than 100% increment, average enhancement increment as compared to the base fluid, which is a very good. It's quite good. It depends to the temperature itself lah, because we have to see the application lah at high temperature or low temperature. And then one of the indicator we have to look at for the nanofluid itself, we have to look at to the pressure drop. So we have to minimize the pressure drop. For example, this for the nanofluid itself, so the baseline, it is about 12% increment as compared to the 100% increment of heat transfer. So we can say that the increment of the pressure drop is insignificant as compared to the increment of the heat transfer. So means that the heat transfer gives better as compared to the drawback in terms of the pressure drop when we are using nanofluid. Okay, so this is something that something that very important lah for the nanofluid topic. So that's why most people they try to to improve again and again using the hybrid nanofluid and also ternary nanofluid. So this is just overview of my research. I don't want to focus on this. And then the future prospect for the nanofluid, you can see that especially for the hybrid and electric car, so we can use the nanofluid for the radiator system to improve the efficiency of the radiator to extract the heat from the system, and also for the electrical appliance in terms of for example the computer, so many appliances need the cooling system. This is some patent granted for this kind of nanoparticle dispersion technology granted in 2017, and also some other awarded. Then just to share a little bit on the research international collaboration with UMP. So this is my university, Mesti Masih Pahang. So we have a various international network all over the world. Even from Indonesia, we have many university. We did the collaboration, have a MOU, and then this is a list of the grant in UMP. Internal grant. It's not a Malaysia grant, a national grant. This is the internal grant UMP. So you see these two international grant. So we have international publication grant, and also we have international matching grant. In fact, for the international publication grant, so I have a LOI, which is I have one grant, which is we do collaboration with KFUPM from Saudi Arabia, Associate Professor Dr. Hafiz. This is the LOI, sample of LOI. And also for the matching grant, so I just received award letter lah, which is collaboration with UMJ. We have one research collaboration lah for the international matching grant UMP. So this is the potential. So I invite everyone, which is we can have a collaboration in international matching grant, also international publication grant. So this international publication grant, they have we have a LOI to make sure that we have a shared publication between UMP and also the targeted university lah. And also, in fact, from Indonesia, so I think you have world-class that have a certain criteria for the professor outside, right? International professor. So also I interested to join this kind of WCP, world-class professor. In fact, when I look at to the criteria for the invitation, outside professor, I also meet all the criteria. So inshallah, we try to, we try to collaborate, we try to apply for the WCP program in Indonesia. Okay. So I think that's all, because the time is quite limited for me to to present, just to give some brief idea about the research topic and also about the research collaboration. So I welcome everyone for any question, right? And also even to ask about the nanofeed and also to ask about the research collaboration and also grant. Then I open for the Q&A lah. So thank you for your attention. So I welcome for any question lah from the audience. Okay, so I left back to the moderator.
Thank you very much, Professor Dr. Wan Hasmi bin Wan Hamzah, for a very nice presentation. I also would like to apologize. I think I give an incorrect title in the beginning of your presentation. So as we already nanofoods, and we have listened that a lot of, I think, potential collaboration that we can develop together with Professor Wan Hamzah about the nanofluids. I believe that the opportunity between ET and UMP also a very, I think, a very great to develop, as we all, as long as I know that we already have the MOU as well, I think, between the UMP and ET. So now I'd like to open the discussion. From the chat room, we already have 2 questions. First, from Linda Yossi. Is a nanofluid can be changed to the solid phase? Because in Indonesia, there is something solid that is put into fuel to the higher combustion energy, but I don't know that the name. Maybe you can respond one by one the question.
Okay. I want to respond on the first question. Is it a nanofluid can be changed to the solid phase? I think it is possible. It depends to the that's why I call as nanoparticle dispersion technology. So it depend to where you disperse to the the nanoparticle to the base solution. So if it is liquid, so we call it as nanofluid. So some people they call as they disperse nanoparticle in the solid form lah. Solid might be gel, right? Is it referring to the gel, or is it gel is not a 100% solid, right? Is it gel or what? Because that one some people they focus on the gel, not fully liquid. So it is there in the in the research world lah. So the people to disperse nanoparticles, good is a nanoparticle because they are using a solid metal type of nanoparticle, metal and metal oxide. So the metal and metal oxide is a high in terms of the thermoconductivity, is very high as compared to the base. So they try to improve the the solution itself, in order by using this metal or metal oxide in order to improve the heat transfer properties or heat transfer characteristics of that solution. So normally we call it as a composite, some sort of composite.
I think we lost the connection again.
One of the issue for the okay.
I think we just lost the connection. Maybe you can repeat
again. Okay. Can I go to the second question? It's all right. Okay. For the
is about the nanofluid already. Is there any implementation in industry, and how is the result?
Okay. So I just want to share my experience actually. Especially for the nanofluid, one of the issue is we got problem when we want to, especially for the nanocoolant, for the heat transfer or cooling system. So the issue is with the cost, because to make it effective in terms of heat transfer, we need to use a bundle of nanoparticle. For example, for 1 liter, we have to use a bundle of nanoparticle in order to increase the heat transfer of that particular nanofluid. So the current technology, if we want to produce, for example, 10 gram or 20 gram of nanoparticle, it consumes a lot of money, cost. So currently maybe the limitation is about the cost, but in the future, maybe after 20 years, it might be we can reduce the cost, then we can implement it in the industry. But I just want to talk on the nano lubricant from my side, which is I just show you one of the pattern itself. And also what happened, I'm trying to actually, what I did is with my team is ongoing to to go to the commercialization. So we already test in the real system, because we try to use that type of nano lubricant in the air conditioning system of the automotive of the car. So from our finding, it confirmed that it can reduce the fuel consumption. It can can perform better. The cars can drive or perform better, and then it's more effective lah. The cost also very a bit it's not that too expensive. So it is possible for the case of nano lubricant, is possible to be commercialized in industry. And also from my team, actually we already implemented, we already tested in the real test car, even in my car. And also we already test in some of the cars lah. We test about 10-20 cars. It is proven, but it is ongoing to go to the commercialization lah. For the case of nano lubricant, for the case of nano coolant, we have a limitation in terms of the cost.
Okay, thank you. I have one short question. Do you develop your own nanoparticle?
Pardon? I'm sorry. Can you repeat?
Do you develop your own nanoparticle?
Procure what? You mean? Yes, I purchase it outside. I purchase from.
Are you developing your own nanoparticle, or you just buy the commercial nanoparticle?
Yeah. What we did right now, we just purchase from the commercial nanoparticle. But in the future, we have one candidate, Miss Arvika, will join my team next semester. So he will study on the synthesized nanoparticle from natural resources.
Yeah.
So we start to synthesize nanoparticle.
Because actually in our group in the ET, we also develop, like, if I'm not wrong, to see your slide in screen, you mentioned about the silica that currently develop the silica from palm oil waste. So I guess it also can be an interesting research that we can do together.
We collaborate with your team later on. we ongoing to do.
I think because we already developed a very established nanofluid dispersion, and I think it will be great if we can collaborate, where we can contribute to develop also in part of the nanoparticles from our biomass waste in Indonesia. But I believe almost the same between Indonesia and Malaysia in the case of the biomass waste. Okay. I'm afraid that the time is very limited, Professor. So we have to finish our presentation here. So before finish, I would like also to once again thanks to you, and the committee have prepared the certificate. Yeah. So Professor Wan Asmi bin Wan Hamzah. Oh, sudah. Oh, okay. Okay. We will email the certificate to Professor Wan Asmi bin Wan Hamzah. So to end the session, let's give a big applause once again to Professor Wan Asmi bin Wan Hamzah. And this is, I think, the end of the session too. I will return back to moderator to close the session.
Thank you very much.
Before the parallel session.
Yes, thank you, Ms. Amanda, for leading this afternoon session. I would like to also appreciate to all the main speakers for today's afternoon session. Ladies and gentlemen, we are now moving to the parallel session. This is what we are waiting for. All the paper presenters who have submitted their research online via ICATCE site have been accepted and also have been accepted by the committees, have the chance to present your papers in this conference. As Pak Rector already have mentioned to you, there are more than 10 paper presenters that would like to have the chance to present their research papers in our parallel session. And this parallel session is divided into 3 breakout rooms. Room A, Room C, and Room B, as you have already seen in the slides. But before that, the committees have set all the presenters' schedule as it is seen in the slides. Please show the schedules of the paper presenters, the schedules in each room, Room A, Room B, and Room C. Perhaps you would like to see it once again. As you can see, there are 1, 2, 3, 4, 5 presenters in Room A. So it will be started in a few minutes. Okay, and our moderator for Room A is Dr. Eng Joni Prasetyo, MT from Universitas Pamulang. And we move on to Room B. In Room B, there are 5 also. Can we move to Room B, Pak Adam?
Thank you, Mrs. MC. How can I join to room A?
May I see your face? Where are you, sir?
I'm the Joni Prasetyo.
Oh, okay. Oh, okay. So yeah, sir. What was your question again?
How can I join to room A?
Oh, you want to choose?
Yeah.
You will be manually choose. So you are given several the options, room A, room
Okay.
B. Later on.
Okay. I got it.
Okay.
Thank you.
Okay. So you can manually choose it between room A.
Okay.
Room B, and room
Yes.
I
Thank
would
you very much.
just a few minutes, a few seconds to show off the room, the schedules of the room. This is room B. Okay, and your moderator is Ibu Ika, and this is room C. There are 6 presenters, and the moderator is Ibu Linda Alivia Yosi STMT. Okay, and the options of your breakout room is already shown off. Audiences.
Where can I know the link for the enter to the like room A and something there?
Oh, it will be showing off. Yeah. So the committees will.
We didn't see here.
Oh, okay. You perhaps have to rename your Zoom account, Pak, so that the operator will move you to the room that you are supposed to attend. Okay. So your your Zoom name should be started from the room. What kind of room do you want to have?
Should we restart again? Yeah.
After that, your name, so that the operator can automatically move you to the room. For examples, you please write down your name, room A, and then your name.
Yeah, I don't know how to get
underscore your name, so that the operator will move you automatically to room A. Okay.
Wait, I don't know name. Where should I write?
You have to rename it, sir.
Rename?
Rename, yeah. If there is an option to rename, you rename it.
Sorry.
Apakah
masih susah ya nih, masih susah Bu nih, gimana masukin ya? Dijeblosin aja deh. nggak kelihatan saya lewat opsi apa ya?
Udah Pak Joni.
Masih di main room nih.
Oh, Pak Joni, Bapak sudah ada di room A. Tinggal menunggu presenternya aja sebentar.
Saya kalau mestinya di sini kelihatan gitu, tinggal background. Oke.
Teman-teman yang ada di sini juga dipersilakan untuk bisa online. Ya, kalau mau butuh wifi-nya silakan di sini. Wifi-nya nama akunnya adalah Sky 30, passwordnya adalah Upper Sky Sahid.
Welcome to this room, Profesor Suhindar Isakumar.
Ya, good afternoon, Pak Pak Anthony. Ya, siap?
Prasetyo, Pak. Saya.
Mr. Pras, kumaha tuh ya?
Kumaha ada mah nggak ngerti bahasa Jawa, bahasa Sunda.
Ke Indonesia apa Inggris nih, Pras? Pak Pras.
Ya, khawatir saya ada ekspatriat yang hadir, Pak. Jadi sebaiknya bahasa Inggris ya, Pak.
Oke. Pak Joni, saya tahunya Pak Joni, Pras. Belum mulai ya?
We have to